you a brief overview on developing robust ceramic thin film materials. And I'll give you a short overview of what we have done in the last years. First, I will start with a short introduction to physical vapor deposition. We use this technique to develop new type of materials, also because PVD is extremely versatile, and thereby you can easily change a little bit in the chemical composition and other important effects like growth morphology. We all know that morphology of materials strongly influence the properties after that. Ceramic materials are by definition, they are hard, right? But what do they miss is very often sufficient fracture toughness. So therefore, we will talk here also about the fracture toughness and how we can improve that of these typically brittle materials. I'll end my presentation with a rather short summary. Good. First, a short overview on physical vapor deposition. Right. What we use is plasma-assisted PVD processes, and we have to treat with homologous temperature around 0.2, because all of these ceramic materials have a melting point of 2000 or even higher degrees C, and the typical substrate temperature that we use is like 400 degrees C, right? And that leaves us with a rather low temperature. And thereby connected is a limited kinetic reassembling during the solidification process. And that allows us to prepare materials with high defect density. And as we people, the defects make us interesting, of course, and also the defects make the materials interesting. And when we tune the deposition properties, we can end up with dislocation densities in a well-known ceramic titanium nitride up to the power of 17 dislocations per square meter, which is really, really high, even higher than heavily deformed steels, which typically have dislocation densities of the power of 16. But other than that, we can also prepare materials with metastable or even supersaturated phases. I will give you some brief overview on that. Typical applications for PVD prepared ceramic coatings are to protect tools used for machining industry or other components. Also in turbine industry, these are used like protective coatings to protect our superalloys against thermal input, like thermal barrier coatings. But here I show you what can happen in simple cutting processes, just depending on the speed that you use. Temperatures at the cutting edge of 900 degrees C or even higher are easily obtained. So the material, what we search for, needs to be wear resistant, of course, but also thermally resistant. So we need to consider also the temperature impact. And we need a wear resistant material. We need a strong material as well as a rather high fracture toughness material. Good. Now start with the defects. Defects like dislocations as I mentioned, in titanium nitride, we could easily end up with dislocation densities in the range of the power of 17 dislocations per square meter. If I zoom here in a little bit, I show you such nice dislocations right here. What we have here is an edge dislocation. We see that there is an additional half plane added to our material, and we find that all over the place, homogeneously distributed, and just depending which parameters we choose for the preparation of these materials. I've added here, sorry, I missed. I've added here the bias potential. We can negatively bias the substrate material, and thereby we attract the ions, and they assist in the bombardment of the growth of these materials. And just by that, we increase the number or density of density of dislocations. I show you here some nice TM studies actually, and that give us a value in the range of 10 times 10 to the power of 16, meaning 10 to the power 7 in dislocations per square meter. If we calculate the mean distance between these dislocations, that gives us a mean distance of 3 to 4 nanometers, meaning that we are close to the theoretical threshold of the maximum number of dislocations in such crystals. So dislocations, we have quite a lot. And I go on with another material system, titanium aluminum nitride. Very successful. Here, we do not just have the high number of dislocations, so we do not have just dislocation strengthening, the Taylor hardening effect. We do have also solid solution strengthening because, as I mentioned, physical vapor deposition is able to prepare supersaturated materials. Here, the aluminum substitutes for titanium in a face-centered cubic lattice that leaves us with slightly variation in the position of the reflexes, face-centered cubic reflexes, meaning they go to higher angles, meaning the lattice parameter itself, right, nicely decreases as what we would expect if we have a nice solid solution, and that provides us typically with higher hardness. So if we start with titanium nitride and we go on with a lot of aluminum, then actually we have hardness increase, right? As I mentioned, just by simple changing of the plasma conditions, we can also tune the hardness of titanium nitride itself. If we increase the number of dislocations and other defects, then of course we increase our strength of our material. And now if we add another element, solid solution hardening, then we make titanium aluminum nitride, then we end up with a very high hardness. If we do that too much, if we add too much of aluminum, then hardness declines, because what ends up is that we change the crystal structure. If we overdo it and we pass the maximum solubility for this type of material, then we end up with the hexagonal structure, and that is weaker in this case. So that's the second strengthening mechanism. Typically what we see from these materials are in the range of 35 to 38 gigapascal hardness. Again, if we like in titanium nitride, change the plasma conditions, we can further boost the hardness. And if we add other elements which do not, which are not soluble in the lattice and then would segregate out during growth of our material, right? Then so they segregate out and form boundaries, silicon nitride, amorphous silicon nitride boundaries. Then actually what we do is we limit grain growth during our growth of the material. That ends up with small sized grains, and then we have even higher hardness. Beyond 40 gigapascal is often seen, right? So we have actually 3 of the possible 4 strengthening mechanisms available in this titanium aluminum nitride. And here I mentioned that we actually can have also the 4th strengthening mechanism, which is precipitation hardening, and that I will show you now shortly. How can we collect the precipitation strengthening effect? As I mentioned, I start again with titanium nitride. We boost the hardness of titanium nitride just by increasing the crystal number, the number of crystal defects. If we would anneal this material, then the crystals become less defected, meaning the hardness decreases to a value where what you would expect if you prepare titanium nitride not by PVD but by other routes, like roughly 20 gigapascal. The titanium aluminum nitride is a supersaturated crystal structure. If you anneal that material, right? I should give you here the phase diagram of titanium nitride, which is here, and then there would be aluminum nitride. Actually, these two have a huge miscibility gap. They don't want to be mixed, but by physical vapor deposition processes, and this is the typical range where these coatings are prepared, between 40 and 66% of aluminum, right? And the maximum temperature, what is used in PVD is 700, 600 degrees C. So that region is deep in the spinodal region of this titanium nitride, aluminum nitride, meaning if you prepare such a supersaturated material, we have that, and then it is exposed to higher temperatures, or you do a thermal treatment, then it decomposes, it spinodally decomposes to form aluminum-rich region as well as titanium-rich regions, both cubic, and as long as these are cubic, then we have actually a hardness increase. We have actually an increase in hardness because we generate these domains here. And these are effective obstacles for the dislocation movement, right? And especially if we have a certain size of these domains. That is a well-known process, actually. Again, if we overdo the annealing treatment, then the cubic one phase transforms into the hexagonal aluminum nitride, and we do lose our strength. But please keep that in mind. We can use this transformation very effective to increase fracture toughness, because here we have a huge volume change, like plus 25% in volume increase, and that is of course beneficial for other strengthening, toughening mechanisms. So now I enter fracture toughness. Strength can be nicely increased by these effects. What about toughness? And the Achilles part of ceramics is actually the fracture toughness. And if we go back to theory and look on Griffith's criteria, what I plotted here is nothing else as these dependence of the critical stress that is available, is allowed before crack is initiated or crack growth. That's here. Our loading here, that is our loading field, and we would be in fracture mode. So, and that is, this plot here is just the logarithmic version of the same Griffith's criteria, right? So what can we do to be in a safe mode? The first thing, it's obvious, because this equation here just gives you two variables, K1C and actually the crack length or the pore size. So these are the only two variables that we have. Y is a factor, and P, of course, is a factor, right? So the first thing, we could decrease the process parameter, like if we would have a pore size or something. If we decrease that, right? If we decrease that, then we can increase by that here, the sigma C, right? And then we end up in a safe mode, which is good. That's the first thing that we can alter. The second one is we change K1C. Change K1C of our material, and thereby we use actually the consumed energy per crack. I will give you some brief information on that. We tested these fracture toughness of thin films actually with a in-situ micromechanical test. That's our thin film, where we flipped out this cantilever here from the film that's around 3 micrometers in thickness. That here is the growth direction, right? And we do that for various processed materials, and we end up in not too high values, right? Typical is 2 to 3 megapascal square root meter. If we would measure our material on the substrate, then we see a much more pronounced effect by the bias potential. And that the reason is the compressive stresses. If we have a lot of compressive stresses, we all know at the surface compressive stresses are nice, because then they prohibit crack initiation and crack growth, and that is exactly what we observed. And if we end investigate various different materials, then what we very often observe is that we have a delta in K1C, roughly 1 megapascal square root meter per 1 gigapascal compressive stresses. You see here 4 for 4. So but that's just a few samples. As I mentioned, we can change the process parameter like pore size. Yes, that is, for example, if we look on sputtered coatings, very often these are rather columnar. And even if we just simply crack our samples before we go to the scanning electron microscopy, then we see nicely this columnar structure, meaning actually we have a pronounced grain boundary failure. If we would investigate just the same chemical composition, but prepared by arc evaporation, where we do have way more metallic ions in the plasma as well. By sputtering, we have basically atoms, no metal ions. Here we have also a lot of metal ions. So if we use a bias potential, we can also collect these and increase the kinetics. So that ends up with a much smoother or less grain boundary failure. And that by itself just increases K1C. And using other elements like those who can strengthen or increase the cohesive strength of the boundaries just are extremely positive in that. So that is one process. The other one I'll show you briefly in the remaining minutes are this transformation toughening. Please remember, we had this example on cubic aluminum nitride going to hexagonal aluminum nitride, where we have this huge increase in volume. Of course, we can use that, right? Microcracks is very effective, and also pores. I'll give you a few examples. This here is a nice study actually by my colleagues in Leuven who used meandering effects and thereby also, of course, the crack deflect, and that consumes more surface, and thereby also the fracture toughness increases to roughly 3 megapascal square root meter. And we started to investigate this transformation toughening effect, where we have these tiny metastable phases, which can then phase transform in a more spacious material, and thereby actually increase compressive stresses at the crack tip, and that nicely is effective on shortening the cracks. That can be seen here, for example, titanium nitride, titanium aluminum nitride, in the as deposited state shows these rather pronounced crack formation. Whereas if we anneal that at 850 degrees C, please remember where we had the precipitation hardening and the formation of cubic aluminum nitride domains, then actually we do miss these cracks. That brings me to another combination. We use this toughening effect and use also coherence strains to other layers to stabilize aluminum nitride in the metastable state. And by that, actually, we have two positive effects. The first one is the phase transformation. The other one is the superlattice effect, which is well known for strength. At a certain bilayer period, we have an increase in strength that is nicely shown by Ulf Helmerson in the early days. And we showed that the superlattice effect is not just good for hardness. On the example of titanium nitride, chromium nitride per purpose, we did not want to have the phase transformation here to study just the superlattice effect. This is also effective in increasing K1C at a certain superlattice period, right? And the reason is that dislocations are influenced by coherence stresses, Orman-like strengthening mechanism, and Hall patch strengthening. And that is what I show you here with the metastable structure as well. We saw that also on polymer substrates, chromium nitride example, just chromium nitride. When we elongate this sample, then we see a lot of cracks here. if we have the aluminum nitride in a metastable state, then we have a nicer, finer crack network, and we see that the cracks at the individual interface is actually deflected. Extremely effective in increasing fracture toughness. Here I started already 3 movies. This is just chromium nitride coating. This is a multi-layer where aluminum nitride is in its stable broadside structure, so no phase transformation possible. And that here, where aluminum nitride is in the metastable state and could phase transform into the more spacious hexagonal structure, right? The crack is formed, but further propagation is hindered, and that is very effective. If loading is too high, of course, everything breaks, and they call this here as the first law of material science. Of course, we all know there is no first law of material science, but in analogy to thermodynamics, I use that here. Everything breaks upon brute force. So there's, but we see that the pieces here, the cracks are stopped, which is an indication that this is a very effective mechanism. I'm already at the end of my presentation time, but I'll show you again this phase transformation right here. And I come directly to the conclusions, right? What I wanted to show is if we need to modify the weakest link, we of course need to know what is the weakest link. Is it the faces? Is it the grain boundaries? Is it the general morphology? And then we need to tune it. We need to know what is the cause of cracking or cause of not so good properties, right? Titanium aluminum nitride is an extremely effective material, but we investigated different strategies to further increase the toughness, and there is superlattice effect, but also phase transformation effect. And I hope I could show you that especially physical vapor deposition is an extremely versatile playground to modify materials. And with that, actually, I thank you very much for your attention, and I thanks for the financial support from industry as well as academia. Thank you very much.